Okay. So, there have been detailed theoretical calculations for NOE. We will not go into those detailed theories, but I just want to show you the results. Okay. NOE, as I said, this will depend upon the relaxation times, and this will depend upon the molecular motion. How fast the molecule is tumbling inside the solution, and that is characterized by a particular time constant known as the correlation time. Okay. For small molecules, correlation times is of the order of 10 to the minus 10 to 10 to the minus 12. This is for nanoseconds. Seconds or nanos, so therefore 10 to the minus, okay, so it is extremely small time. Seconds, so that means it is the order of nanoseconds, right. So, and for this is for small molecules. And correlation time can be of the order of 10 to the minus 8 to 10 to the minus 9 for large molecules. So, this basically reflects how fast the molecule is tumbling inside your solution, and the relaxation times will depend upon this. Okay. Now, according to that, so the theoretical calculations on NOE have been done, and it turns out that the NOE is equal to, if we want to represent this as Nxa, and A is the one which is perturbed. In the earlier case I wrote it as Nix, A is the one which is perturbed, and Nx is the X is the one which you are going to monitor, and this is typically equal to half gamma A by gamma X, where gamma is the gyromagnetic ratio. Okay. And it all depends upon the individual spins also. Okay. And this will be different for different situations. This is for this condition, this is for this condition. Okay. So, therefore, what will be the kind of NOE? This is the steady state NOE. Steady state NOE means I do an experiment in the, as I indicated to you before, the experiment is done in this manner, that I have FID collected here, and I do a pre-saturation perturbation here on one particular line. On a particular line, let us say I do it for the spin A, and I monitor the spin X here. Okay. So, when I perturb here, I monitor the intensity, and without the perturbation I monitor the intensity, and then I take the ratio, I get the NOE, and this will now by calculations one can show that this is proportional to half gamma A by gamma X. What is the advantage here? So, the advantage is, suppose A is proton, suppose A is proton, okay, and X is, let us say, carbon 13. What is the ratio gamma A by gamma X? It is 4, right. So, therefore, and therefore this NOE will be a factor of 2. If gamma A is equal to gamma X, then of course it is a factor half. So, this is 0.5. This is an enhancement. How much is the enhancement in the intensity of the lines? Then when you perturb one spin and observe the other spin. And if you are perturbing proton and observing carbon 13, then means you are getting a factor of 2 enhancement in the intensity of the line. Okay. So, and that is the significant advantage. That is the significant advantage, because the factor of 2 enhancement, meaning it is like a factor of 4 in terms of the time with respect to the signal averaging. Okay. So, therefore, the steady state NOE, this is the steady state NOE which we call steady state NOE. And in the, this limit is called as the extreme narrowing limit. This is the small molecules, very rapid motions, and this is also called as extreme narrowing limit. Here the tumbling is very rapid, the motions are very fast, so the averaging happens much better, and the relaxation times are also very different. So therefore, without going into the theoretical details, this is to just to show you what kind of a thing is it will look like. Now what will be the situation when we are in this large molecule range? The large molecule range, it turns out that this is equal to minus gamma A by gamma x. For large molecules Nx A is equal to minus gamma A by gamma x. Okay. So therefore you can see for proton, if A is equal to x, then this Nx A is equal to minus 1. Okay. And if I want to plot here the NOE as a function of the correlation time here, it will look like this, and this is my 0.5 and this is my minus 1. So this is the case for homonuclear systems. So you have minus 1, so the negative NOE you will get, this is called as negative NOE, but nonetheless it is a kind of a significant change in the intensity, and when you take the difference you will get a substantial enhancement. And for large molecules you will get a minus 1 as this one. But if it is not homonuclear, then of course you have gamma A by gamma x, that is proton and nitrogen or something, then you get a factor of half also, and then you will get minus 5. So you get heteronuclear ones, of course you will have a different number, for it will be minus 4 something like that, minus 5 for proton or nitrogen, because this is well, nitrogen has another complications in the sense that the gyromagnetic ratio for nitrogen is negative. Okay. So therefore there, even for the small molecules there is the gamma A by gamma x. In the case of nitrogen it will be negative. Okay. So this is what I showed here in the previous slide when I said half gamma A by gamma x. You see here, if you are talking about nitrogen, proton nitrogen NOE, and then let me also draw that here. If let us say A is equal to proton, then x is equal to nitrogen 15, then this nitrogen 15 has gamma of nitrogen is negative. So therefore you will get a negative enhancement there, and that will be a factor of 5, because gamma A by gamma x there is 10, and therefore divided by multiplied by half, then you get a minus 5. So even in the extreme narrowing limit, when you are talking about heteronuclear NOE, proton nitrogen, it is minus 5, and proton carbon it is plus 2. So these are the factors one has to remember when studying these experiments in the steady state NOE. Now there is another experiment, so far I talked about what is called as the saturation, pre-saturation. This is called as one saturation was done on the spin A, and we are monitoring the spin X. There is another way one can do, and that is called as transient NOE. Transient NOE. What you do here is your perturbation will be like this. You do the experiment like this. Okay, let me draw this by a different color. This one I will put like this. So this is a selective perturbation, selective inversion. and this is a hard 90-degree pulse. This is a 90 hard pulse. What does that mean? So then let us say I have a spectrum something like this. So what I will do is I will selectively invert this line. I will selectively invert this line up to a 180-degree pulse. This is 180 degree. So I will selectively invert this. So then I will get here this one like this, and this remains like that, and whatever happens here, and I give a time here called tau m, and tau m is the so called mixing time. So what I have achieved here? Okay, let me explain what we have achieved here. So this is the experiment. Okay, what happens? So let us assume that I have the initial magnetization of all the spins. All of these have different magnetization components, right. Let me draw the x, y, z. So draw the magnetization of this particular spin here, and the magnetization of the other spins also will be here, let us say. Okay. So during the period when I apply selective 180-degree pulse, what I am achieving is I am inverting this magnetization. I am selectively applying a selective 180-degree pulse on the black line, which means the magnetization which was here is now like this. When you measure it, of course I will see it as a negative signal. Now this is the perturbation, this is the perturbation. This perturbation has to recover back to equilibrium. The system will have to recover back to equilibrium. What it will do? It will relay this perturbation to some other spins which are close by in space. So then this will relay. So as it recovers like this, it will relay this magnetization to some other spins. Okay. So therefore what will happen is these components which are present here, they will also get little bit of that component. The red one which was there, red one we will also get certain contribution from the, let us say like this, a contribution, and the black of course is recovering down there. So the black is slowly recovering. So it has come, let us say, then of course certain contribution of the magnetization has gone. Do not assume that the certain portion of the black, it is transferred that to the red. Okay. So therefore this will show up when I measure it, it will show up in this some intensity of the red one. If this were a red one, that would have gone down or it would have gone up, either way. It can happen for both positive and negative NOEs. You saw already that for small molecules it is positive NOE, which means it is an enhancement. For large molecules it is the negative NOE, means that it will decrease, intensity will decrease. So therefore there can be changes in these other portions of the spectrum as a result of the inversion here, and I give certain amount of time here tau m because I am allowing it the magnetization to transfer. This is dependent on the relaxation time. Depending upon the relaxation time T1, the efficiency of transfer will vary. Therefore this can go to different ones as a result of the dipolar coupling between the two spins. So therefore when I measure this, I will get different intensities of these lines here, not all of them but some I will get, some I do not get. No, something will be perturbed, some will not be perturbed. Okay. So now if I take the difference here, if I take the difference between these two, this fellow has not perturbed, this has perturbed, this has perturbed, and maybe this has not perturbed. Let me take it up there. This is not perturbed. Okay. So then I take the difference. Difference is equal to what I will get? I will get a thing here much larger. Let us say this minus this, then I will have a 0 there, and this I will see minus there because this is increased, this is small, perturbed, and this also I get a minus here, and then I get 0 here again, no perturbation, right. These are the perturbed ones, these are the NOEs. Okay. and this will depend upon the mixing time, this will depend upon the mixing time. How much time do I give? Why does it depend on the mixing time? Because it depends on the relaxation time of the perturbed spin and the relaxation times of the other ones also. Now once I have done this, will it always remain there? Will it remain at that point only? Question is, let us say I have a molecule like this and I have a proton here, a proton there, a proton here, a proton here, a proton there, so on and so forth. I perturbed one of these fellows, I perturb this fellow, then it will relay from here to here because it is closed directly during the T1 T1, but this is also now perturbed. As a result of this is also perturbed, therefore it will also have to relax. What it will do? It will also transfer to something which it is close by. So let us say I have I take that, so from here it will go here, take one more, or it can go from here to here, or it can go from here to here, and so on and so forth. So what is this phenomenon called? This phenomenon is called as spin diffusion. Okay. Spin diffusion means the magnetization which is perturbed at one point, it will keep diffusing through your network of coupled spins, and that will obviously depend upon the time tau m. So this will depend upon proportional to tau m. Larger the tau m you give, longer will be the spin diffusion. Okay. And therefore if you restrict the tau m to a very small value, then it will go only to the directly neighboring spin. So if I were to plot, so if I want to plot the NOE as a function of tau m, then it will go like this, it will come down. So this is the linear, this is called the linear regime, during which time it is directly proportional to the neighboring spin only, going to the neighboring spin only, and it is in this region one can calculate interproton distances. From the NOE intensity. Okay, here the NOE intensity is proportional to what is called as the cross relaxation rate, which is represented as sigma, and this is proportional to 1 over Rij to the power 6. So if I say sigma ij, so this is proportional to 1 over Rij to the power 6 in this approximation, in this region. In this region it is proportional. If we go beyond that, because the intensity, NOE intensity is no longer just restricted to that, it will start diffusing to other ones. So the relaxation, individual coupling between all the spins will come into the picture, and you may not be able to do it. Therefore transient NOE is an experiment which is done with a controlled manner. You can control the extent of diffusion that can happen from one spin to another spin, and that is the extremely useful parameter for calculating the structures of molecules. And this is the basis of structure calculations in macromolecules. This is for short tau m, okay, and there it is restricted to the near neighbor interactions only. For short tau m, the transfer is restricted to near neighbor interactions. Therefore, so polarization transfer has two objectives, right. So two objectives, polarization transfer by NOE has two objectives. So therefore NOE, in summary of the time, NOE has two gains. One is and hence signal intensity of less sensitive nuclei. This is like carbon 13, nitrogen 15. And the second is derive structural parameters of macromolecules. So, these are two important applications of NOE, and we will not go into the theoretical details of this much more than this. I think that is adequate for our purpose of structural biology, which is the focus of this, because otherwise it can get very complex. Okay. So, now let me take one more topic. Okay. So, we will take another topic here, which is called as selective population inversion. You consider a 2-spin system AX, A and X. This can be heteronuclei, can be homonuclei also. And what I will have? I will have here a simple 2x spin system will have, A will have 2 lines and X also will have 2 lines. Okay. Let me draw the energy level diagram for this. I will have 4 states. Let us say the population of this is delta plus delta, population of this is minus delta plus small delta, and this one is delta minus delta, and this one is minus delta minus delta. Okay. So, now I call this transition as A1, this transition as A2. Call this as X1 and this as X2. Okay. Now, let me draw the intensities of the A transitions. Intensity of the A transition is population, this population minus this. So, therefore, that will be 2 delta. And similarly, the other one also A2. So, if I call this as A1, this is A2, and both these have intensities of 2 delta. And what about X1 and X2? This is this minus this. So, I will have smaller intensities, and notice here delta is greater than delta, okay, and this is 2 delta and this is also 2 delta, and this is my X1 and this is my X2. So, now what I do is I invert this transition, invert selective population inversion, this is what I said, selective population inversion. So, now what will be my intensities of the 4 levels? Now, I will draw these levels again here. This population becomes this. So, this will be minus delta plus delta, this will go there delta plus delta. Okay, I am inverting only this, I am not changing anything else. So, this will be delta minus delta and this will be delta minus delta. I am not doing anything here, I am not perturbing these populations at all. Okay. Now, I see what happens to the transitions. What happens to the transitions? The 4 transitions, these were my A1, A2 transitions, and the X1, X2 transitions are these X1, X2. What will be the intensities here? Let me draw the A1s first. and this is now minus 2 delta. Okay. The A1 will become minus 2 delta, change the color here. Okay, this became minus 2 delta, and this one is this minus this will be plus 2 delta. Okay. So, this is my A1 and this is my A2. What about the red ones? Red ones are these. So, delta plus delta minus of delta minus delta. So, minus delta plus delta minus delta minus delta. So, that is minus 2 delta plus 2 delta. So, this is minus 2 delta plus 2 delta, and the x2 is 2 delta plus 2 delta, 2 capital delta plus 2 small delta, right. So, that is this plus this minus this. So, 2 capital 2 delta plus 2 delta. See, look at this. What was small 2 delta here, 2 delta here has become this large. Quite a substantial enhancement in the intensity, although the gain is not the same in both cases. That is, but nonetheless each one of them has gained substantially in terms of the intensity of the lines. You have, at the cost of the magnetization of the A1 transition, you have got the enhanced intensity for the X transitions, enhanced intensity for the X transitions. Notice here these A1 and the A2 transitions have become completely opposite to each other, antiphase. This is called as antiphase. They have become antiphase. The A transitions have become antiphase because they inverted only one of them, and therefore Iska intensity is changed. So, one is minus 2 delta, other one is plus 2 delta. In the earlier case both were 2 delta, and I have inverted one of them, therefore that became, one of them became minus 2 delta, other one remained the same as 2 delta. And with the x1 and the x2 transitions, which were initially both equal as 2 delta and 2 delta, the one of them has become minus 2 capital delta plus 2 delta, and the other one has become plus 2 capital delta plus 2 small delta, and you see substantial gain in the intensity, right. So, therefore, this obviously will depend upon how much is the individual difference between capital delta and small delta, and that is dependent on the gamma of gamma of A and gamma of X. Okay. So, that is proportional to the ratio of the gyromagnetic ratio. So, the gain is proportional to this is this depends upon gamma A by gamma X. Okay. So, the gain will be proportional to the ratio of this gyromagnetic ratios of the two. So, substantial gain can be obtained if it is heteronuclear. For single homonuclear systems it may not be that much of an advantage, but heteronuclear it will be a great advantage. This principle is used in other techniques which we will take up next time, and that is particularly useful for all multidimensional multiples experiments. So, the important thing of course to notice here is that you may call this as a disadvantage, while there is an advantage which you already discussed. The disadvantage could be that you have positive and negative signals. You can say the disadvantages would be you have one positive and negative signals. Second, you cannot decouple A and X, because if you decouple the two will collapse. When they collapse you will get back the same intensity. Okay. Only when the coupling is present, the two lines are separately observable, then you gain the advantage. So therefore, and you want to get rid of both of these kind of a situations, and that leads us, brings us to other techniques which is called as insensitive technique. And of course, in the third disadvantage also could be selective inversion requires long pulses, that means it will not be 10 microsecond pulse, it may be millisecond pulse. Okay. If depends on the selectivity what you will want to observe. So the better the selectivity you want, the longer the pulse length will be. Therefore, and this is a difficult thing to achieve, and then the fourth selectivity is may be difficult in complex spectra. So while the gains are there with regard to the intensities, we also have certain disadvantages here. To get over this, we go into some other techniques which are called as inept, and that will be taken up next, and in fact that will be the most crucial thing for all multidimensional NMR experiments. So I think we will stop here.